So, acceleration. We're going to do three things. Determine when, or describe motion, okay, when there's a change in velocity. When there's a change in velocity. Where you compare, compare graphical representation of accelerated motion. And then finally, apply kinematic equations. So, first, acceleration. Our definition for acceleration is the rate at which the velocity of an object changes. Think about it. When you drive a car, isn't the gas called the accelerator?
Yeah.
Because it makes your speed go up and down, doesn't it? Yeah. Well, speed and velocity are analogies. So when there's a change in velocity, it means you must be undergoing some sort of acceleration. Right? Some sort of acceleration. So since we're looking at the rate at which velocity changes, rate means divide by time. If I want the rate at which this water flows out the sink, I determine how many gallons come out per minute. So I might put a bucket underneath the sink, right? Have this going into the bucket, time it for a minute, figure out, okay, it's a half a gallon, so 0.5 gallons per minute. That's called the volumetric flow rate, because it's per minute. Acceleration is change in velocity per unit time. So what we're going to see here is that my units of acceleration, well, what are the units of velocity? Those are meters per second at the very top. The units of time are given in seconds. So I have meters per second. So it's meters per second squared. These are your units for acceleration. These will be utilized all year long. Okay, even if you're doing things like one-dimensional motion, two-dimensional motion, projectile motion. Okay, if we're looking at forces and accelerated motion on a ramp, you're going to use these units. So again, this is your unit for velocity. But since acceleration is velocity over time, or change in velocity over time, we take meters per second, and you get meters per second squared. What does the delta mean for this? Well, delta means really just VF minus VI. That's really what this formula is telling us to do. Okay, we've used this term VF for final velocity. We've talked about the term VI real quick. But specifically, let's outline it here. So your change in velocity is final minus initial. Your change in position is your final position minus your initial. It's always final minus initial. Okay? All right. Let's take a quick look at an example. Pablo, nice and loud for us, please.
The shuttle bus slows down at an average acceleration negative 1.8 miles per second.
Square.
How long does it take the bus to slow down from 9.0 miles per second to complete stop?
Okay, so meters, be careful. Miles would be MI. Okay? So meters per second in this case. So we clearly can see that we have some sort of braking mechanism. How do I know that the bus driver is braking? How do I know, Alejandro?
Because it's going to be at a negative velocity.
Yeah, take a look at negative acceleration. Negative acceleration, that means you're slowing down. Right? If I had a positive acceleration, I'd be speeding up. I also know that it's coming to, or using the brakes because it says how long will it take the bus to slow down from 9 meters per second to a complete stop. How do you stop? You stop by hitting the brake. So, the gas pedal is an accelerator. What would you call the brake pedal? A decelerator, is what you're going to say? A decelerator, okay? So they're both methods of accelerating. One is just negative acceleration. So let's go ahead and listen. And that's why we have a case. All right. Let's go ahead and list our givens. What's one of our givens right away? What's one of our givens in this problem? Katie. Your acceleration is negative 1.8 meters per second squared. Very good. Now, this entire year, I will state this right now, we are going to deal with constant accelerations. So we're not going to have acceleration initial and acceleration final. That's the acceleration throughout the entire problem. Okay? What else? What else? Anthony.
I was going to say we can determine the velocity
Okay, so initial or final, which one?
Well, they give us the initial, well, we also know they give us both really.
Give me one of them.
9 meters per second is the initial velocity.
And the final velocity, somebody else? What's the final velocity in this problem? It's not obvious, but it kind of is. Pablo?
0, just stop.
Yeah, comes to a stop, 0. Okay, it's not stated, that's the thing. So you have to use your context clues. When it says complete stop, that means your final velocity's got to be 0. But it nowhere says that the velocity is 0, but stopping means your velocity is 0. So we've got the information. What are we looking to do? Figure out. Ellie, what are we trying to figure out here? So what's that variable, Ellie? What variable are we looking for? What variable represents how long something takes? Don't look at your nose, think logically. I don't need the letter, but tell me in general. Yeah, good. Time. Change in time. Okay, so our goal is to figure out the time period or the delta t. We've got a formula, don't we? So we've listed our givens. We've listed our desired variable. Klaus, what's the formula from the last slide?
Delta t times.
You can flip through the last slide. Slide up to your last slide and tell me what it is. What do you have for the formula? Just give me the general formula.
It's delta t over delta t.
Very good. So delta, oops, I just put a t. Acceleration equals change in velocity over the time period. There's our formula. Now, what is our goal? What are we trying to find? So what can we do? Good. And then how do we get rid of acceleration? So in reality, what did I tell you about the v equals x over t formula? What can you always do when a formula is written with this setup where you have something equals a fraction? You could flip-flop these. Remember we talked about this last class? This is why you don't want to have to do this every time. Multiply by time, brings it up here, and then divide by acceleration, bringing it down here. So literally switch these two positions. Okay? So we've got time equals change in velocity over acceleration. Well, our time period equals Vf minus Vi over acceleration. That's what change in velocity means. So, why is it important that I put Vf minus Vi? Can anybody figure it out? Take a look at when you plug in numbers at this point. Class.
That would be negative 9.
Yeah, we need this to be negative. Why do we need this numerator to be negative 9? Because you're slowing down, and what's your denominator going to be then? It's also negative. What's negative divided by negative? And time needs to be positive. So if you switch this by accident, you would have 9 minus 0 over negative 1.8, which would give you a negative time. Doesn't make any sense. Okay? Formulas need to be written correctly. So we go ahead and plug in. Change in time or time period equals final minus initial over acceleration. Sorry. So we've got 0 minus 9 over negative 1.8. Yep. 5 what? Seconds. How do you know it's seconds, Natalie?
Well, because if you cancel everything out, you're left with seconds.
Yes, you're right. When reducing dimensions, you get seconds. You should know time is measured in seconds because everything's standard units right now. So, if I were to really evaluate the dimensions behind this, just look at dimensions, okay? You're taking dimensions of meters per second. Why do I put the brackets? To indicate dimensions. I'm showing you dimensions on the right. Over meters per second squared. When you divide by a fraction, it really means multiply by the reciprocal. So if I was really analyzing these dimensions even further, if I'm dividing meters per second, whoops. If I'm dividing meters per second and I want to divide that by meters per second squared, I multiply it by seconds squared per meter. Remember, when you divide, and I'll show you what I'm pointing to. Fraction divided by a fraction means take that first fraction, multiply by the reciprocal. Meters cancel. Seconds squared over seconds. The second squared cancel with that second, leaving behind simply seconds for units. Okay, so you can always check your units by simply performing that operation. Okay, it's a unit dimension check. Questions on this problem? Craig?
How did you get the, oh, is it because it's a squared, so, I figured it out. I got it.
You sure?
Yeah, I figured it out.
Okay. Other questions on that? Relatively straightforward example, right? Would you agree? I call those plug and chug. Plug it in, chug on through the problem, right through. Okay, if it's not an easy problem, it's going to be like a multi-step problem. Or maybe you have to solve for acceleration in part A, utilize that acceleration in part B, and determine the displacement. Okay, that's a little bit more involved. So this is an easier one. Okay. At some sort of a graphical analysis. So take a look at this graph. Let's zoom in a little bit, actually. Let me make this graph a little bit bigger. All right. Look at this graph here. Velocity versus time. How is this different from yesterday's graph? Or last class, I should say. How is the graph different? What graph did we look at last time?
Wasn't the graph last time constant?
What do you mean constant? Oh, it had like straight lines. Agreed. This has curved lines. Good. That's a good first part. Last time it was straight lines, whether they were positive, negative, or zero slope. They were straight lines. What else is different? Yeah, wasn't this like displacement versus time or position versus time? This is now velocity versus time. So bear with me for a second. Okay? I'm going to point and I want you to follow along. And you can jot down words if you'd like to. So at this point in time, what's the velocity of the particle? 0. Because it's at the origin, isn't it? Now, what's happening to the velocity? It's increasing, isn't it? How do you make your velocity more in a car? You hit the acceleration, the gas. We're going to talk about that in a moment. So in the beginning, since the velocity is increasing, we have positive acceleration up until point A. So let's jot that down, please. There's definitely positive acceleration from here to here. Positive acceleration. Well, take a look. What's the slope of that line? And you're not going to be able to calculate the slope, but generally speaking, is the slope positive, negative, or 0? Positive. So, remember how last time we identified that the slope of the last graph was like the velocity? Well, the slope of velocity versus time graph is going to be like our acceleration here now. Well, we continue this problem, right? We continue looking, we see that it's still positive slope. It's still positive slope until we get to here. What's the slope now at point B? What does neutral mean? 0 slope. If there's 0 slope here, it means that in this range right here, I'm going to cover that with like a black horizontal line. In that range, the velocity is blank. The velocity is blank in that range. I'm asking you, tell me, fill in the blank. Fill in the blank. The velocity is constant. Better word. Good. I don't want to say still, because still implies not moving, right? So, in the beginning, the velocity is increasing, increasing, increasing. Then, the velocity is constant. The object is still moving. Constant velocity just means that you hit cruise control, right? That's all it means. So, I'm going to act out from A, from the beginning until the end of what we've shaded. So, here's what's happening. Faster, 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 faster. Slower, slower. Oh, no, sorry, I shouldn't say slower. The velocity, let me do that one more time, gets faster and faster and faster and faster until it reaches now moving constant. I need more room here. Okay, but it speeds up in the beginning, and then from some point in time, where the black horizontal line begins, to another point in time, that object moves at a constant velocity. There is no acceleration, because what's the slope of that graph? What's the slope of a horizontal line?
0.
0. So at this point, the acceleration equals 0. We could write that the velocity equals a constant. Over here you had positive acceleration, so the velocity was increasing. And it's crazy because we don't even have an acceleration graph. We have a velocity graph. Yet we can see what the acceleration is by looking at the change in velocity. Because change in velocity is acceleration. How about the third leg, the easier part, now that we've done the first two? How about this third leg of the trip, which we'll leave in red the way it is? Ellie. Negative acceleration. How do you know that? Because the velocity is decreasing. In this entire range, the velocity keeps going down. It fluctuates a little bit, right? But generally speaking, the velocity is going down. So the acceleration is negative. Okay, so we went from positive acceleration to zero acceleration to negative acceleration. And we did that by analyzing the graph, or by simply looking at the slope of the line. Look at the slope of the curve. If the slope of the curve is negative, acceleration is negative. So let's jot that down at the bottom. Slope of a v versus t graph is acceleration. Not to be confused with the last time we said that the slope was velocity, because that was a different graph. That was position versus time. Okay, so the slopes of graphs are extremely important. I could give you a linear function that you could calculate the slope of and simply say, determine the acceleration of the object at time A. All you need to do is find the slope, and you have the acceleration. Okay, that's for velocity versus time graphs. Don't confuse this with position versus time graphs. Position versus time graphs, the slopes of those are velocity. Well, the slopes of velocity versus time is acceleration. Okay, if you go on to take calculus, you'll learn in calculus specifically how these things are all related. All right? We want to fill in this table. There are a lot of blanks here on the table, right? A lot of blanks. Our goal is to fill the table in. So, what is one way that an object can speed up? What is one way an object can speed up? Give me an example. Sarah. You could push it. So, all right, you know what? I'm going this way, and I want to go faster, so somebody has to push me in that direction, right? Or I need like a little rocket booster behind me that shoots out some sort of energy to push me forward. That's what a car really is doing, except it's using an axle and turning an axle, which turns an engine. A little bit different. So if I'm moving in the positive direction, right? The only way to speed up is if the acceleration is also, let's say positive. The velocity would be increasing, right? The acceleration would just stay positive. Now, what if I'm moving with a negative velocity? Right? I'm moving with a negative velocity. I want to get faster. What kind of acceleration do I need? I want to get faster and faster and faster. So I'm getting faster in this direction. So what kind of acceleration would that be? A negative acceleration. So if your velocity is to the left or negative, and your acceleration is to the left or negative, you're technically speeding up still. But you're speeding up in the negative direction. Does that make sense? We're going to go over when you're slowing down in a moment. Think about it. If you're moving this way, you want to go faster, you need to push that way. If you're moving this way, you want to go faster, you need somebody to push you that way. You need acceleration that way. So, if acceleration and velocity are the same sign, you are speeding up. That's our conclusion from the first part here. When these are the same signs, you are speeding up in both cases. How about slowing down? How about slowing down? How about slowing down? Class. Very good, class. Well done. Why is that? Somebody else explain. Why is that, man?
Let's say a positive velocity.
Okay, a positive velocity.
When you slow down, it's basically the acceleration is pushing against you, which is the other way.
I'm slowing down and then I stop, right? So acceleration has to push me that way if I'm moving that way in order to slow down. But if I'm moving this way, right? Now, if I'm moving this way, which way does acceleration have to push me to slow me down? Yeah. So if I'm moving negative, my acceleration is then positive. Okay? So as Klaus mentioned, opposite signs. Opposite signs indicate slowing down. How about constant velocity? When do you have a constant velocity? Right? That's what I'm doing. Constant velocity. What do I know for sure? If I hit cruise control, am I hitting the accelerator anymore? It's cruising, isn't it? So constant velocity indicates what? What?
It's the same initial velocity and final velocity.
So therefore, what?
No acceleration.
Zero acceleration. The velocity can be positive or negative to start. Doesn't matter. If I'm moving this way with no acceleration, it's a constant velocity. If I'm moving this way with no acceleration, still a constant velocity. Doesn't change the matter at all. Okay? Now, how about the next part? Speeding up from rest. Speeding up from rest. If you're starting at rest, what do you know about your initial velocity? You're starting at rest, speeding up from rest. What must your initial velocity be? Sierra? Zero. It's got to be zero. But if you're going to speed up, right, I'm at rest right now. The only way I can speed up is if I do what? Start moving. To move, though, from zero motion to move at all, aren't I increasing my velocity? So you need some acceleration. So speeding up from rest means you start at zero, and acceleration can be positive or negative. Either one works. But you need some sort of acceleration. The last and easiest one to fill in. Good. How do you remain at rest, right? No velocity, no acceleration. I'm standing still. Make sense? Okay? What kind of a question would you expect on a test? Would this be three options? Multiple choice, short answer, which is like theoretical, or mathematical? Probably multiple choice, right? An object is moving, blah, blah, blah. And this is what happens. Determine which of the following is true. The object is speeding up, the object is slowing down, the object is moving at a constant velocity, the object is not moving. Right? So anticipate the kind of questions on your test so you have an idea of how I'm going to quiz you on this kind of stuff, or test you on this. Alright. Now, we are going to go over three equations of motion here. Okay? Three equations of motion. And they're called kinematic equations of motion. They're kinematic because they involve some sort of motion themselves. So the first one that we started with was this. You can write, actually you can write this down if you want. We wrote this down a little while ago, right? Now, if I replace delta V with VF minus VI, and I go ahead and solve for VF, this is a standard equation. How do I get rid of the T? The T is currently dividing. It's going to go somewhere on the other side, but it's currently dividing.
Oh, they multiply.
So then you multiply, right? Always do the opposite. Multiply both sides by time. On this left-hand side, you're going to have acceleration times time. On the right-hand side, you're going to have VF minus VI. Remember, these times canceled. How do I solve for VF? How do I get rid of a minus VI? What do I do to get rid of a minus something? If there was a minus 5 on the end, how would I get rid of it? Add it over. So we end up getting VF equals VI plus AT. This is one of our big three formulas. And we write it on the formula sheet because it's used a lot, but it really comes from the acceleration formula. It's just a manipulation of that. Okay? So that's one of the big three formulas we're going to use. And again, it comes from this formula right here. For the sake of time, I'm going to list the other two. Okay, I'm not going to derive them and show where they come from, but your book does derive them in the text. Or you could look to see where they come from. You're welcome to do that. The other two are the following. Displacement equals initial velocity times time plus 1/2 acceleration times time squared. You're not going to have to memorize these. They're on your formula sheet. But trust me, you will end up memorizing them just by doing enough problems. The third formula to utilize, VF squared equals VI squared plus 2AX. Now, tonight, listen carefully. So we've got a race car and it reaches a speed of 42 meters per second. It then begins a uniform negative acceleration using its parachute and braking system. And it comes to rest in 5.5 seconds. Find the distance that the car travels during the braking period. So, beginning any of these problems, it's like I have no idea where to start. And I don't, unless I list my givens. And then I can go from there and say, all right, what formula works with these givens? So what are the givens in this formula? What are the givens? Honor?
1 meter.
Is what?
The highest speed.
Which speed? Initial, final, and why?
The initial. Well, is it final because it reaches a speed?
It seems like it's final because it says it reaches a speed, so you think it's like speeding up. But then when you read the rest of the problem, you realize that it's eventually stopping. So 42 is you're right, the initial speed. Okay? It is the initial speed, VI. Now, if a car is moving, right, and it's driving at 42 meters per second, and its speed is 42 meters per second, and it's going that way, its velocity is also considered 42 meters per second. So this is one of those times that the words speed and velocity are interchangeable. Because this car is literally driving, it's a race car, it's driving straight down. It's going at 42 meters per second, it finishes the race, the parachute ejects out the back, it hits the brakes, it has to stop. Okay? So this is the initial speed because the process starts after it reaches this speed. That's the hard part about physics, because the wording can become very confusing. You want to think that because it says it reaches 42, that 42 would be the final velocity. But it reaches 42, and then the problem begins, really. It then begins a uniform acceleration. So the problem starts from when the person in the car has already gotten up to 42. So that's initial. Theo? Yeah, give me another given. Go ahead.
0.
What is?
The final velocity is 0.
How do you know?
Because it's stop.
Okay. It comes to rest in 5.5 seconds. The minute you see comes to rest, you know VF is 0. What else do we know? I just read it.
Comes to rest in 5.5.
So what's the variable for that? Yeah. Okay, variable for time is t, 5.5 seconds. So that's the info we've got. We know the acceleration is negative, but do we know its value? Do we know the acceleration's value? Look at the problem. We don't. We don't know the acceleration's value. That's unknown. But we're not asked for that. What do we ask for?
Distance.
The distance. Find the distance the car travels during braking. Well, if I'm driving a car and I start to hit the brakes right now, and then I travel 1, 2, 3, 4 steps, that's 4 meters about. So the distance traveled after braking is the same thing as the displacement. So really we're looking in this problem for x. And we have several choices of formulas now. We've got formulas starting with VF equals VI plus AT. VF squared equals VI squared plus 2AX. And x equals VIT plus 1/2 AT squared. Katie, what are we trying to find?
First you have to find the acceleration.
Why?
Because you need to plug it in
Why?
to find distance.
Yeah, look at displacement. And I know you saw it, but I want to make sure we all clearly see this. Look, you're trying to find x, aren't you? What is needed to find x? VI. Do you have it? Do you have t?
Yeah.
Do you have a?
No.
So we can't use this right away. How about this x? You have it? So we can't use this one either. So these two are pointless right now because we have two variables unknown. But we could use the first one to find a, and then use a in these two to find x. If I could find a in the first one, or even use the formula from the other day that says this, the same thing as the first one here. Those are identical, but it's already solved for A. So use this one. Remember, these formulas I'm showing you here with the arrow are identical. VF equals VI plus AT is the same thing as A equals delta V over T. But the formula A equals delta V over T is already solved for A. And we're trying to find A. So we should probably use the one at the bottom in red instead of the one at the top that is also given. These are both on your formula sheet. So on your formula sheet right now, in the margin, next to this formula, I would personally write, utilize this when VF is not involved. Right? That's when this one is. No VF involved. Here, when time is not part of the problem, you're going to use this one most likely. And here, when displacement is not part of the problem, you're going to use this one. So it depends on what you have. You got to go list your givens, list the desired variable, go through the formula, see what you know. If you know everything in the formula, except for one variable, and that's the variable you need, then use that formula. So let's go ahead and figure out the acceleration first.
Wait, why do we need the second formula? Like, what's not involved?
Where? Here? There's no time involved in that one. So acceleration equals final velocity minus initial velocity over time. What kind of an answer am I going to get? What kind of an answer? No, not units, but what kind of an answer? A negative answer. How do I know that, Klaus?
Because it's negative on top, but positive on the bottom.
Yeah, mathematically, and then from the problem it says negative acceleration, and you're braking. The minute you hit the brakes, it's going to be negative acceleration if you're going in the positive direction. So 0 minus 42 is negative 42 over 5.5 gives us negative 7.6. So I am never going to be calculating. That's up to you guys to do in class. So when I wait, okay, and I ask a question like that, I expect all of you to have a calculator around to be doing it. So please take that out now because we have 3 more problems today still. So take out a calculator now at this point. The reason I really am annoying about this, and I'm going to be very annoying if you don't have a calculator, is because so many students sit there and don't do the work in class and let others do it, and then on the test, they make careless mistakes in their calculator. Do all the math right on the test, and they may make a mistake plugging it in. So you need to be checking this work while you're in class. Okay? So that means you need to be bringing a calculator to class. Some of you recognize that from the quiz, and you really struggled in the quiz without a calculator. Bring a calculator to class. So that's your acceleration. If that's your acceleration, what formula can I then use to find x? And there are 2 answers. One answer is better than the other. There are 2 answers here. One answer is better than the other. Sierra.
The last one?
Why?
Because it'll give you x directly.
Exactly. X is solved for in this equation. You could use the one above it. You could use VF squared equals VI squared plus 2AX. You could definitely use that. You'll get the same answer, but you would need to rearrange it to solve for x. Why do more work, right? Take the shortest route possible. Use the one that's circled in blue there. So let's go ahead and plug in what we know in that formula. In this formula, we know x equals VI. What was VI? 42. Hold on, let me just put units. Times the time. 5.5 plus 1/2 times negative 7.6 times 5.5 squared. You can do it in pieces and put this number here and this number here, and then add them together. That works, but you could also just do it all in one line in your calculator. Please do it all in one line in your calculator. All in one line of your calculator. Do it all. Use parentheses around 1/2 if you're going to write a fraction of 1/2, or just take negative 7.6 times 5.5 squared divided by 2. Okay, but please do this. Don't just sit there. Do it. Because when you get it wrong in the test, I'm going to have very little sympathy. You know what I mean? Okay, if you're not practicing in class. And if for some wild reason you forgot your calculator today, you better have the next class. Because this is attempt number 2 at everybody having calculators. What do we get for x? What do we get for x? What do you got, Pablo?
210.1.
210.1. Be careful. I got 210.1, I think, for this one, right? Isn't that what this part becomes? Isn't that what 210?
I got 116.
Yeah, 116.05.
You got 116.05? Others agree? Yes, no, maybe so?
Yeah.
Okay. So to the nearest, we'll say 116 meters. Now, just to demonstrate something real quick. When I did this myself and I came up with my own answer, I used negative 7.63 repeating for acceleration. Because that's what it was. Remember earlier we calculated acceleration? It was really negative 7.636363. So I used that. And when I used that down here, actually, I ended up getting 115.5. And a lot of you said 116.05, right? You got? So that little deviation is called a propagated error. And that's okay for now. But I recommend that on tests, unless it's your final answer, you do not round earlier. You follow? So here, I would have used negative 7.636363, maybe 5 or 6 times, right? Calculate it, then round the final answer. Okay, because when we round earlier, like we rounded the acceleration earlier, it becomes a little bit off the answer you want to get. It's a propagated error. Propagated just means something that is cumulative. It's a little error in the beginning, creates a bigger error in the end. Imagine how many people like to play video games like Call of Duty or Halo. Nobody? Just one guy in here or 3 people? Okay. Well, you know those first-person shooter games? If you're off by a tiny bit and you're using a pistol, right, and they're close by, it doesn't really matter much. But if you're using a sniper and you're off by a little bit, smallest deviation with a sniper over 1,000 yards is a big deviation, right? It's a propagated error. It's the same thing this is really. So if you're close range with one of those pistols, or you play Halo or Call of Duty? So I say you're using BR or a pistol from 1 or BR from 2 or 3. So say you're using one of those close range, right? A small deviation doesn't matter. But if you're really far from something, a little error has a big effect on the problem. That's what this kind of thing is here. Okay, a small mistake or a small rounding error here creates almost like a half of a meter distance. Half a meter, it's about this big. It's a big error in the end, right? Okay, so try not to round to the end, but for now that's fine. Questions on the first of 3 problems for this section of 2.2. All right, good.
Like the 3 that we're going to be using for problems.
Whenever there's anything involving acceleration, notice acceleration is in all 3. Whenever, bless you. Whenever there's acceleration involved, is that 3 or 4?
She does that.
She does it every class, every day, every
It's not
time.
perfect.
It's an
It's not-
attention
No,
grabbing.
it's not. I see.
How do you stop the sneeze?
Yeah, you can't stop the sneeze. I mean, it's different. It's I do know that, I remember in my last grade student who would sneeze extremely loud.
Is it Siobhan?
You can control that. No, that's school, right?
Oh.
But you can control that. You can't control the sneeze 3 times.
Siobhan, at the end of her sneeze, seems to find it necessary to do a nice squeal. I'm like, what are you doing? You can suppress that, okay? That's suppressible.
So these problems involve acceleration. If there's no acceleration in the problem, and you notice that there's no change in velocity, you go back to section 2.1 where we use v equals x over t. Okay? All right, this one. Let's see. Emma, what do you read for us? Nice math, please.
A plane starting at rest at one end when run by undergoes a uniform acceleration of 4.8 meters per second squared for 15 seconds before takeoff. What is its speed at takeoff? How long must the runway be for the plane to be able to lift off?
So we got 2 parts of the problem, right? We want to know what its speed at takeoff is and how long the track or the runway should be. Now, the hardest part of these problems is recognizing what the beginning and the end is. So, a plane starting from rest. What does that tell me?
0.
0 what?
Meters per second. The its initial velocity.
There it is, yes, in meters per second, very good. So VI is 0, so that's the beginning of the problem. It then undergoes some acceleration for a given time period. We then want to know what the velocity is as it's taking off. So we're solving for what? Final velocity. So this problem starts when the plane is at rest and ends when the plane is about to take off. Real life, it doesn't end there because the plane takes off and it continues and it flies and it goes on. But our concern is to know what the velocity is when it takes off. We need to know that value so that we can figure out how long the runway needs to be when we construct that runway itself. Okay, when that runway is constructed. So here's a simple problem that some engineer might have to simply calculate so they know how long to build a runway based on the planes. When else is this really important? Really important. Think about where else can planes take off from?
Aircraft carriers.
Aircraft carriers. Aircraft carriers in the water, there's no land. So what happens if you screw up and you don't take off in time? You're in the water. An aircraft carrier has runways that are specifically made so that planes that take off from them can take off right before it exits the aircraft carrier. Okay? So you need to get up to a given velocity. Now, there's some new cool stuff that they're doing. I don't know if anyone has seen this, but with these, what's the term? I need to know what the name is. It's like, it's called an electromagnetic gun. And the way it fires particles is it fires them using a magnetic field. The magnetic field is able to accelerate things a lot faster than, say, a rocket booster. So they're trying now to create aircraft carriers that are shorter in length because they use this EM pulse or this EM force to launch the plane at a higher velocity. So normally an aircraft, some sort of a plane, a fighter jet, could accelerate really quick. But with this EM gun or this technology, which is really like a maglev train, the trains in Japan, it uses that technology to accelerate the aircraft faster so that it can take off on a shorter runway. So they've been building these ideas now in these new aircraft carriers. So let's take a look at this one. So let's start givens. We already know that Theo told us this. And we know that because it says right here, starting at rest. We then know it undergoes a uniform acceleration of 4.8 meters per second. So what should I write? Yeah, second squared. I said second, my bad. Second squared. Now, that is positive. Therefore, it's going to speed up the plane in the positive direction. If it were negative in this case, you could have negative acceleration. It would just be going that way because it wasn't moving to start. So if you're at rest, remember from yesterday the table we filled in? If you're at rest and you undergo negative acceleration, it just means that you're going to accelerate that way. That's all. You're not braking at this point. If you were moving this way and you undergo negative acceleration, you're braking, you're hitting brakes. But if you're starting at rest and it's negative acceleration, it just means you go left. Okay? Alright, what else do we know? What else?
Time.
What is the time, Sarah?
15 seconds.
Alright, so we've got three things. Three things. Frankie, tell me, what are we looking for in this problem?
The speed at takeoff.
Yeah, so what would we call that variable, Ellie? VF. What else are we looking for in this problem? What else? Yeah, we're trying to find how long the runway would be. So we'll call that displacement. X, displacement. So we're looking for two things. We're looking for two things. We've got a couple formulas to choose from. Instead of reiterating these formulas every time, look at your formula sheet if you need to, or go to the last slide. There are three formulas. They will help us to discern, figure out what these values are. So which one will we use to figure out what VF is? Sorry. Yeah. So to find out VF, let's utilize this formula. VF equals VI plus AT. Tell me why we can use this formula. Why can we use this formula? Katie.
Because it gives you straight away.
It gives you?
Straight away what you want.
Yeah, it gives you what you want solved for, right? Here. But it also recognizes that we know these, don't we? Don't we know VI and A and T? We know all three of those. They're given right here. So simply plug them in to get VF. This is probably the easiest. Remember I said plug and chug? This is plug and chug right here. You plug in, you're done with the problem. The last example, you need to find the acceleration as an intermediate step to find the answer. Notice that your units have to match up, people. Meters per second plus, this is really just meters per second. Because it's meters per second squared times seconds. Okay, this right here, this A times T quantity, its units are meters per second when simplified. Because this second cancels with one of these, leaving meters per second, which is adding to meters per second. If you ever add two numbers, they have to have the same unit. If you ever subtract two numbers, they have to have the same unit. When you multiply two numbers, their units can differ. Okay? But because I'm adding 0 meters per second to something, the units here have to be meters per second. What do I get? What do I... 72? Did everybody get 72? I also got 72. Step 1, done. We're done with the speed of takeoff. How about the next part of this problem? The next part, Katie.
X equals VI T plus 1/2 AT squared.
Now, there's another formula we could use. Why aren't we using VF squared equals VI squared plus 2AX? Sierra?
Because it gives you displacement right away.
Yeah, this formula gives you displacement and you know everything in it. Only because we know everything in it can we use it. We might as well use it because it gives us X. So go ahead and plug in now again. Initial velocity is 0. So watch what I'm going to do. Everybody look up real quick. I do this a lot, so I want you to recognize. That means this value drops off. It goes to 0. It's just a term you're going to see a lot of physics and math teachers do. When there's a part of a formula that doesn't involve, or is not involved because VI was 0, what's 0 times 15? 0. So this whole portion doesn't matter. So put a diagonal arrow and put a 0, meaning this goes to 0. It has no value, no problem. Okay? So the 1/2 AT squared is all that matters.
Oh, you don't even to answer.
Yeah, you don't even need the 0. Just drop it off completely.
I got 112. What did I do?
Did you square your 15 first?
Oh, yeah.
Don't forget to square the 15. Make sure 15 is squared first, then multiply by 4.8, then multiply by 1/2. You can't multiply those three numbers, then square it. Okay? Or if you forgot to square 15, actually, that's probably what you ended up doing, right? Yeah. Okay, but again, make sure you do not multiply these three numbers and then square it. PEMDAS, right? Start with parentheses. Well, inside the parentheses, nothing can be done. Then go to exponent. So square this first, then multiply. Recognize that your units make sense. If I square seconds, it's second squared. Second squared cancels with second squared, leaving behind
Meters.
And what am I finding? Displacement. Meters. So it makes sense. Your dimensions always make sense. Okay? Well done. Well done. So I'm glad that you're all answering and all focusing. Very good. Good section. So 540 meters is how far, or how long, rather, the runway needs to be. It's a pretty long runway. It's like, what? A football field is 100 yards. A meter is a little more than a yard. So this is more than 5 football fields in length. So this is more of like, probably like a Boeing 747 that takes off from a regular airport. Probably not an aircraft carrier. If it's an aircraft carrier in a jet, that's way too long for an aircraft carrier. I don't know. 5.5 football fields is a long aircraft carrier. I think that'd be too much. Yeah, go for it.
A person pushes a stroller from a velocity of 3 meters per second, uniformly accelerating at a rate of 0.5 meters per second squared. What is the velocity of the stroller after it has traveled 4.75 meters?
Now, by process of elimination, since it's the last problem, a lot of you are going to guess which formula we're going to use. But let's prove that we're going to use that one that we haven't yet. Okay, so let's list our givens first. What do we have for givens here? Honor?
VI was 3 meters per second. And then
How do you know that?
because it says from velocity,
And also because what are you trying to find?
the final velocity.
Okay, so if you're trying to find the final and you're given another velocity, most likely it's the initial, right? Okay, good. What else? Somebody else? Emma?
The acceleration.
Is?
4.5 meters over second.
Good. Meters per second squared. Very good. What else? What else? What else? Sarah?
Displacement is 4.75.
And as we saw, we're looking for final velocity. We have x, we have vi, we have a. That's one formula that works really well for this. Okay, and it's vf squared equals vi squared plus 2ax. It's not only a nice formula because it's already solved for vf, but it's really a nice formula because we know everything else in the formula. So this is just a plug and chug here. I'm going to just move the whole screen over, sorry. So I'm literally plugging in the 3 numbers on the left there. The 3 meters per second for VI, the 0.5 for acceleration, the 4.75 meters for displacement. Now, look at your units. Everybody, real quick. Meters times meters is meters squared per second squared. This is meters squared per second squared. So we could add these two numbers together in the end. And we're going to get meters squared per second squared, but then we're going to have to take a square root. So it's still going to come out to be meters per second. Okay, so let's go over to that to make sure it's clear. Two times a half is just 1. That's easy. Okay, now I add those numbers together, which gives me 13.75 meters squared per second squared. But I have to recognize that those units are all squared and annoying because my value on the left is also squared. So I get rid of a square by doing what again? Square rooting both sides. So to get VF by itself, it's the square root of 13.75 meters squared per second squared, which make my units just meters per second. Right? If I square root a square, what happens? They cancel. Right? The square root of m squared and the square root of s squared is just ms. Square root of 13.75. 3.7. People agree? Now, one thing we have to point out, though, is when you take a square root, you actually get plus or minus always. Right? The square root of 25 is normally 5, but it could also be negative 5. Negative 5 squared is back to 25 still. The square root of 16 is 4 or negative 4. The square root of 100 is 10 or negative 10. Because when you square negative 10, you get back to 100 still. So we have to put a plus or minus symbol in front there, please. It's not important right now. You know why it's not important right now? Because we know that the answer is going to be positive. We started, ready? Let me analyze this with logic now, not math anymore. Logic. You started with a positive velocity. I'll point, actually. You started with a positive velocity here. You undergo a positive acceleration. Imagine me walking in the positive direction and you pushing me forward with a positive acceleration. It's going to make me go faster. So this answer of 3.7 is going to be positive for sure. But we have to recognize that there is an option of plus or minus. Then we use our logic and say, well, although there's a positive or negative answer, we are using the positive answer for this problem. The reason you have to recognize the negative answer, free fall. I drop the pen, ready? I catch it here. The velocity when I catch it is going down. So the velocity is negative. So sometimes I'll have a negative answer depending on the nature of the problem. okay, depending upon the nature of the problem. I still have 7 minutes. I would like to start section 2.3. Okay, I'm doing this to save us time in the next. Okay, that's why I was telling you yesterday you're welcome to get a head start. You have 5 problems here. No, 4. Well, 4, but 1 has 2 parts. The lab for you guys is also, yes, due tomorrow. Okay, that's one you knew about since last week, or since Monday? We did lab Monday, yeah.
Tuesday.
We did the lab on Tuesday?
Yeah, we did it actually pretty
We
late.
did it Monday because we had double physics.
Yeah, it was Monday. So yes, lab due tomorrow, so finish up what you need to finish up, and homework 2.2 is due tomorrow. Remember that next week your test is on Wednesday. So that problem set is due on Tuesday. So over the weekend, you might want to get a head start on the problem set also. So let's get a look at section 2-3 now.